Welcome back everyone. In today's session we are going to start exercise 1.3, which is one of the most important exercise of this chapter for 4 mark. Okay, you may get a 4 mark question from this, or you may get other questions too. So the first question can be asked in 4 mark. The other questions can be asked in 3 to 2 marks. So by the way, this is one of the most important exercise of this chapter. So before we go for the first question, let's recall what we learned about irrational numbers. So we learned that all non-perfect square numbers like root 2, root 3, root 5, okay, 7, 11, these all are non-perfect square numbers, okay, and these all are irrational numbers. We learned it in previous class. And all the perfect squares, root 4, root 9, root 16, these all are rational numbers. These are rational and these are irrational. So we already know that these are irrational numbers, non-perfect square numbers, but here we are going to prove it by indirect method, that is contradiction method. So I'll explain you today how to prove that root 5 or any of these numbers. If I explain you the one, then you can try the other one on your own. So before we go for that, let's recall even the primes and twin primes. So you learned about primes. What are prime numbers? You learn about it. Numbers which has 1 and itself as a factor. Like example, what are the prime numbers? 2, 3, 5, 7, 11, 13, 17, 19. There are 25 prime numbers from 1 to 100. So these are the prime numbers. You can observe that all the numbers, when you find the factors, they'll have only 1 in itself as a factor. I discussed about this in the previous exercise also. So the factors of 19, if I see, 19 goes in 19 table only. 13 also goes in 13 table. 13 won't go in any other table, isn't it? So that is the reason these all are prime numbers. So there are many prime numbers. Then what are twin primes? What do you mean by twin primes? Twin primes are the primes which differ by 2. What are twin primes? Primes which differ by 2. Like I can say from the above examples, 3 and 5, you can say 3 and 5, I can say 3 and 5 are twin primes. This just I am giving you an extra information about primes and twin primes, okay. So 5 minus 3 is how much? 2. So 3 and 5, this 3 and 5 form a pair of twin prime. Then 5 and 7, what do you say about 5 and 7? 5 and 7 are also twin primes. Like this we have many twin primes. 17, 19 is also a twin prime, because 19 minus 17 is 2. Is 13 and 11 a twin prime? 11 and 13, what do you say? Yes, even 11 and 13 are also twin primes, because 13 minus 11 is also 2. So this is the meaning of twin primes. So we learn about primes and we have also seen twin primes. Now let's see another term which is used in this exercise, that is CoPrimes. What are CoPrimes? Now with the name you may think that CoPrimes must be prime. No, nothing like that. CoPrimes need not be prime. coprimes can have any number in it. It can have even composite number in it. So coprimes are, this is the main thing I want to explain you, because this is going to, we are going to use this coprime concept in our question number 1. So what are coprimes? Coprimes are the numbers, they can be any number, not only primes, which has only one as a common factor. Like if I take an example, say 25 and say 36. So are these two divisible? Are these two still divisible by any number? No. 25 we cannot divide, 25 and 36 we cannot divide it further. This is simplified form. So I can say 25 and 36 are coprimes. Like you used to write a fraction in simplest form. Like if I take an example, 18 and say 16. 18 and 16 are divisible by 2, isn't it? I can divide it by 2, 2 9 times, 2 8 times, then I get 9 by 8. Now they are not divisible. 9 by 8 are not further divisible. So this 9 and 8 are also coprimes. This is also a coprime. 25 and 36 is also a coprime because they are not further divisible by any number. What is the common factor in them? The common factor, I can divide them by one table. Yeah, the common factor in them is 1. If I write the factors of 9, it goes like 3 3s are 9 into 1. And if I write the factors of 8, 2 into 2 into 2 into 1. Yeah, so there is no common factor. That's the reason we cannot divide. So what is the common factor between 9 and 8? That is only 1. Yeah, and the common factor between 25 and 36 is also 1. We cannot divide them further. Yes, so like this there are many coprimes. So coprimes are the numbers which has 1 as a common factor. They are not further divisible by any number. Got it, everyone? So what do you say about 15 and 16? Are they coprimes? Are they coprimes? Yes. Why they are coprimes? Because they are not further divisible. Okay, let's continue with it now. Next, we are also going to see this theorem. This theorem is also used in question number 1, that is exercise 1.3. So if p is a prime number and p divides a square, okay, let's take one example of a prime number like 5. Suppose 5 divides 25 square, isn't it? 5 divides 25 square. 25 square is 625 and 5 divides it, isn't it? Then p divides a also. Yeah, the theorem is if p divides a square, then p divides a also. This is our theorem. Okay, so here I am taking a as 25. Okay, that is if 25 square is divisible by 5, the 625 is divisible by 5. Yes, then 25 is also divisible by 5. Okay, if 25 square is divisible, then I can say 25 is also divisible by 5. Okay, this both are true. So in place of a I have taken 25 here and our p value is 5. So if the square of any number is divisible by any other number, then the number itself is also divisible. Another example, if I take 2 square is divisible by 2. Then I can say 2 is also divisible by 2. There is no doubt in that, isn't it? If I say other examples also I can take, there are many examples. Okay, so just to remember this theorem, that if p divides a square, then p also divides a. So these are the things which we are going to use in the solving first question. We are going to use CoPrimes concept, and we are going to use the concept of this theorem. So let's continue with the exercise question now.